So you can start, sir.
Okay. Very good afternoon, dear students. Today we are going to see the very important topic, that is a disk scheduling algorithm. Now, basically, before proceeding for the algorithm, different algorithm which are in the topic, that is disk scheduling, we would like to see that why it is required, what are the different components, what is seek time, what is rotational latency, and whether the seek time is is required as a minimum or maximum, that we are going to see. So the operating system is responsible for using the hardware efficiently. Everybody knows that the main objective of the operating system is to keep the CPU as busy as possible. Along with that, one more responsibility which the operating system is taking is the using of the hardware in a efficient manner, so that there won't be any problem as far as the hardware is concerned. For example, disk drive, that means having a faster access time and disk bandwidth. So see here, whenever as a user, what we want from the computer, that the processor should execute my instruction or my program with minimum time, with faster access, and the number of, what we can say, the access to the disk should be minimized. So these two are my requirements. So in order to cope up, in order to fulfill the requirement, this requirement of the user, the operating system has to play a very important role in executing the user instruction in efficient manner with the help of efficiently using the hardware, or what we can say, the disk drive, or the other component of the hardware. So if you see the access time, what is the meaning of the access time? Access time is the time required to, what we can say, access the particular program or execute a particular program output. So it has two component. First one is the seek time. It is the time for the disk to move the head to the cylinder containing the desired sector. So everybody knows that the hardware part, that is the disk drive, secondary disk, we can say secondary memory, which consists of the sectors and the track. So what is the meaning of the seek time? It is a time for the disk to move the head, particular head, to the cylinder containing the required sector. Whenever we want to access the particular data, the data is stored on the particular sector. So seek time is the time taken to move the head of the cylinder on the particular sector. And what is the second component, which is again very important as far as the access time is concerned? It is a rotational latency. So it is the additional time waiting for the disk to rotate the desired sector to the disk head. So again, as the name itself indicates, it is a rotational latency. Latency, again, it is a time spent. It is the additional time wherein waiting for the disk to rotate the desired sector to the particular disk head. And as far as the seek time is concerned, yes, surely it should be minimized. Seek time is equivalent, almost equivalent to the seek distance. And the disk bandwidth is the total number of bytes transfer divided by the total time between the first request for service and the completion of the last transfer. So if we simply calculate the total disk bandwidth, so it is the total number of bytes which we are going to transfer divided by the total time between the first request serve and till the last byte is going to transfer. So these are a few, what we can say, the terminology in the disk scheduling. So in continuation with this, see here, what is the disk access time? It is a seek time plus rotational latency plus the transfer time. So if we calculate the disk time entirely, so seek time everybody knows, it is the time for the disk to move the particular head containing the desired sector. Then rotational latency, additional time waiting for the disk to rotate the desired sector to the disk head. One more parameter, that is the transfer time, the time required for transferring the bytes. And what is the disk response time? It is the total of disk delay plus queuing, means all the programs which are in the queue, plus the seek time plus rotational latency, and finally the transfer time. So these two are very important points we need to consider while going for the DIC scheduling algorithm, that is the DIC's asset time and the DIC's response time. There are many sources of the DIC's input output request. What are the different sources for serving the DIC's input output request? First one is surely the operating system. The means ultimately the operating system is the different resources, different programs of the operating system, then system processes, and finally the user processes. These three are the sources for fulfilling the IO request. And the CPU is not there because we know that in the previous lecture we have seen that CPU cannot manage the input output as well as the external event, and that's why the CPU is going to send the particular process into the waiting state when there is a input output in the form of the external event. Input output request, it includes the IO mode, disk address, the memory address, the number of sectors to transfer. So whenever there is an external event occur in the form of the input output request, so what does it consist? It consists of the disk address, particular disk address. Surely the memory address must be there, the number of sectors to be transferred. So these three are the major parameters or the factor or the what we can say the entities in the input output request. OS maintains the queue of requests per disk or the device. It is the responsibility of the operating system to maintain the request and per disk per device. Idle disks can immediately work on input output request. Busy disks means work must be in a queue. So if you see this, the last point, that is optimization algorithm only makes sense when the queue exists. So whenever we have the number of requests to be addressed, to be executed as far as the disk is scheduling. See here, I have created a fine number of the programs, and then I send that programs to the for the execution purpose. So it comes from new state into the ready state, and from ready state it goes into the running state, and the CPU dispatcher will take it from ready to into the running state. So in order to execute this five process in an efficient manner, in an optimization manner, we have different algorithm, and the optimum algorithm is going to help in execution of this process in a faster manner as far as the DIC's scheduling algorithm is concerned. See here, as we have seen in the previous lecture, we have seen the CPU scheduling algorithm, different CPU scheduling algorithm. So likewise, in that context only, there must be a different algorithm which is going to help to the operating system in order to give the optimum result as far as the DIC scheduling is concerned. Means how the DIC is going to schedule, or how the DIC is going to execute, store the output, that we are going to see using the different algorithms. Now the DIC structure. Disk drives are addressed as large, one-dimensional arrays of logical blocks where the logical block is the smallest unit of transfer. One-dimensional array of logical block is mapped into the sectors of the disk sequentially, wherein the sector 0 is the first sector of the first track on the outermost cylinder. Mapping proceed in order through that track, then the rest of the track in that cylinder, and then through the rest of the cylinder for outermost to the innermost. So this way the internal working of the disk takes place. Now we are going to see the different algorithms of this disk scheduling. So in the previous slide, we have seen the seek time, then rotational latency, then the response time, the delay time, everything that we have seen. Now, exactly we are going to see the algorithm, different algorithms of the disk scheduling, which helps in order to, what we can say, fulfill the request. For example, we have this queue 98, 183, 37, 122, 14, 124, and 65 and 67. Let us consider that this is the queue request that we need to address. And let us consider the head of the cylinder is at point number 53, or head start from point number 53. So this thing we are going to see. Note that the drive controller have smaller buffer and can manage a queue of input output request. Several algorithms exist to schedule the servicing of BICS input output requests. The analysis is true for one or more many platters. See here, the first algorithm that we are going to see is the first come first serve. As we have seen the CPU scheduling algorithm, wherein we have seen different algorithm, and one of the algorithms was first come first serve. This pattern is same, the concept is same, that is first come first serve means which comes first, the request is going to serve first which entered into the system first. So the queue is 98, then 183, 37, 122, 14, 124, 65, 67. And what is the current head position? It is 53. So what is the total size of these discs is 0 to 199. Total number of cylinders are there. This is the total number of cylinders. So why 199? We know that the sectors start from the 0 1, means the numbers should start from the 0, but why 199? So as far as the queue is concerned, the highest number request is 183, so we generally consider 199. So it is not mandatory that we should have 199 always. Means we consider from 0 to 199 likewise, or 0 to, for example, 299 likewise. It is not mandatory, but for our assumption we are considering it. So from this head, that is 53, it starts. Then as far as this first come first serve algorithm is concerned, what is the as the name itself indicates, it is going to satisfy the first request in the queue. What is the first request to be addressed? The first request to be addressed is 98. So the head will move from 53 to 98, serve it, then see the queue. The next request which is in the queue is 183. So from 98 it will go directly to the 198 183, because that is the second request in the queue. Then from 183 it comes to 37. Why 37? Because that is the third request, third priority request in the queue. So likewise, if you see the queue 98 to 67, as far as the first come first serve algorithm is concerned, it is going to serve all the requests as per the queue. So finally it is going to serve 65 and then 67. So if we calculate the total number of cylinder, total number of head movement in terms of unit as cylinders, then it comes to 64. So how we have calculated 64? The first with the head is at 53, then it moves to 98. So because why it has moved to 98? Because that is the first request. So 98 minus 53, likewise we are going to calculate 183 minus 98, then 183 minus 37. Likewise, when we calculate the difference of the head, total head movement in terms of the unit as cylinder, it comes to 640 cylinders. So that is the outcome of the first come first serve. So first come first serve, a few points that we are going to see under this algorithm. It handles the input output request sequentially. Why? Because it is going to serve the request which comes or which entered first. So surely it is going to satisfy the request in a sequential manner. Then fair to all processes. Why it gives fair to all the processes? Because there is no concept of what we can say the priority as far as the first come first serve is concerned, that we have seen in the CPU scheduling, wherein we have seen the first come first serve is purely based on the concept of the non-preemption, means which comes first served first. It never depend upon the priority and other things. So fairness as far as the opportunity is concerned, so equal opportunity to all the processes. Approaches random scheduling in performance if there are many process per request. So if there are many process per request, then it goes for the random scheduling. And finally, suffers from the global zigzag effect. Why the first come first serve is suffering from this? Because the request which comes entered first, it is going to serve. Let us consider the request is like first is the head is at 10, then the request which comes first in the system is, let us consider, 400. Then the third request come is for example 8. So instead of moving from 10 to 8, which is very closest, which is very which takes very less time if it serves 8, but it is not going to serve 8, because the concept of the first come first serve is the request which entered first into the system is going to serve first. So instead of moving from 10 to 8, though it takes less time and the difference is very small, distance is very small, it first served the 400 request, and then from 400 it again comes to 8, and then let us consider there is one more request which comes into the system is for example 12. Then go to 12, let us consider there is one more request, that is 500, then go to 500, likewise. So it suffers more as compared to other algorithm in a zigzag effect, and that's why when we are going for comparison as far as the optimization and better result, that we are going to see which algorithm gives the better result. But as far as the first come first serve is concerned, it suffers from the global zigzag effects. And one more thing, in the first come first serve, it never take the direction into the parameter. Means, let us consider that we are at head number 53. So in other algorithm, we have the opportunity to move in the left direction or in the right direction. Again, that is not a mandatory. So we can take that decision. But in case of the first come first serve, we do not have any concept as far as the direction is concerned, whether to move towards the left direction or towards the right direction. Now the next algorithm that we are going to see is shortest seek time first, SSTF, shortest seek time first. Here we have seen in the CPU scheduling shortage job first. So shortage job first means the job is going to execute which takes smallest CPU burst time. So likewise, shortest seek time first and shortest job first of the CPU scheduling is almost same. Concept is same. So what happen in SSTF? It selects the request with the minimum seek time from the current head position. Means before proceeding, maybe towards left or maybe towards right direction in the disk, it has to calculate what the minimum seek time. So here see the difference in the first and this algorithm. In the first one, we never go for calculation of the seek time, which one is maximum, which one is a minimum. The request which enter first into the system, we are going to serve it. But in case of the shortest seek time first, from the head position, we need to calculate what are the minimum seek time, the minimum distance before proceeding to serve the request. So select the request with the minimum seek time from the current head position. The shortest seek time first scheduling is a form of shortage of scheduling algorithm, may cause starvation of some request. See here how this starvation occurs in the shortest seek time first algorithm that we are going to see. So in case of the shortest seek time algorithm, that we know that the from the current head position, it is going to serve the request which has minimum seek time, which has minimum distance. Ultimately, seek time means we are considering the minimum distance of the head position from the head position. Let us consider that there are 3 requests and the current head position is at 3 requests, 25, 80 and for example 85, and the current head position is 50. So from current head position, it is going to calculate whether the 25 is close to this current head position 50 or 80 is close to current head position. So likewise, it is going to move. Let us consider that one more request come into the system and which has minimum seek time from the current head position, then it is going to select that one. Let us consider so many requests are coming simultaneously, and all have, what we can say, all have minimum seek time from the current head position. The time comes wherein the request which entered at first, which has smallest arrival time, is not going to execute, because of the concept of this algorithm that find out the minimum seek time instead of finding out that which entered first. So because of this concept, there is a starvation. And that we now the next thing we are going to see, the shortest seek time algorithm. Select the request with the minimum seek time from the current head position. It also known as, it is also called as the shortest seek distance first, SSDF. Sometimes there is a twisted question in the examination. What is shortest seek distance first? So shortest seek distance first, SSDF, is same as that of SSTF. It is easier to compute distances. It is biased in favor of the middle cylinder request. Yes, it is biased because it is little bit difficult. Means let us consider that what we can say, if the distance from the head position is same, then it will be difficult to go in which direction, whether to proceed with the left or right. SSTF scheduling is a form of shortage of first and may cause the starvation. Now see here, this is the snapshot for the same queue: 98, 183, 37, 122, 14, 124, 65, and 67. And what is the current head position? Current head position is 53. Now start from the 53. Now see the difference in these two algorithms. In first come first serve, it will move directly from 53 to the first request, that is 98. Whereas though 98 is the first request it enters, but it is not going to serve. It is going to first find out what is the minimum seek time. So 53, 37 to 53 and 65 to 53, which one is minimum? The difference distance from 53 to 65 is minimum, so it is going to serve 65. Then 65, which one is minimum? 67. So likewise it is going to calculate. So 67 to 37, again reverse the direction, then go serve 14, then again reverse the direction from it has started from left to means from current head position to the right, then moves to left, then again go to the right. So likewise it is going to serve 183. See here, the question may be why it is not going to serve 0 and why it is not going to serve 199. So these, though we have considered in this entire disk, we have considered 0 is the starting location, whereas 199 is the final one. But there is no request as such, that is 0 and 199 in the queue. But it is not the reason that why we are not going to serve it, because in the coming algorithm wherein there is no request like 0 and 199, still we are going to serve, because that is a requirement of the algorithm, that is the concept of the algorithm. Now, and if you see the difference as far as the total head movement of the first come first serve, in first come first serve the total head movement is 640, whereas here in the shortest seek time first, as the name itself indicate, shortest seek time SSDF, it is 236 cylinders. Now the next concept, next four algorithms, that is a scan, look, C scan and C look. This belongs to the concept of the elevator algorithms. Algorithm based on the common elevator principle. Everybody knows the concept of the elevator. Four combination of the elevator algorithms. These are the four. Means out of these six algorithm, that is first come first serve, SSTF, scan, look, C scan, C look. These four belongs to the elevator concept. Service in both the direction or in only one direction, means it is going to serve either in left or right or in both the direction, and go until the last cylinder or until the last input output request is going to satisfy. So from the diagrammatical representation, we come to know that the scan algorithm go until the last cylinder. It is going to serve the request in as far as the last cylinder is concerned, and it may serve in both the direction. Now, what about look or C scan? C scan is go until the last cylinder is going to satisfy and service in only one direction, maybe the right direction or maybe the left direction. And what about the look? Look go until the last request is going to satisfy. Instead of the last cylinder, it is going to satisfy the last request. It is not going to touch the last cylinder. It is going to satisfy only the last request. And it may go into both the direction, maybe towards left or right. What about the C loop, circular loop? Again, go until the last request. Again, it is not going to touch the last cylinder and serve only in one direction, maybe towards the left or maybe towards the right. So see the difference between these four algorithms. So scan and C scan, it is going to touch the last cylinder, whereas the difference is scan service both the direction, C scan service only in one direction. Look and C look, circular look, go until the last request is there in the queue. It is not going to touch the two ends or might be one end of the disk, and service in only one direction and service both the direction. This shows the difference between the scans, C scan, look and C look. Now we are going to see the first algorithm of the category elevator. The disks start at one end of the disk and moves towards the other end, servicing request until it gets to the other end of the disk. Here, see the difference. See the concept of the scan. It starts at one end of the disk and moves toward the other end, servicing all the requests until it gets to the other end of the disk, where the head movement is reversed and servicing continues. Sometimes it's called elevator algorithm, and now we are going to see one example wherein the total head movement are 208 cylinders. See here, same queue, that is 98, 183, 37, 122, 14, 124, 65, 67, and head start at 53. Now 53 head start. Now you may have a question, why towards the left and why not towards the right? That I have already cleared you that it is not mandatory that whether to move from 53 to 37 towards 37 or 53 towards 65. It may move from 53 to 65 or it may move from 53 to 37, which is already there in this snapshot. So start from 53 because that is the current head position, move toward the first request. It is going to serve all the requests which comes in the path and till it reaches to one end of the disk. And now what is the one end in that direction? The one end in that direction is 0. So it is not a circular linked list concept. It is not a circular scan. The scan algorithm is going to touch any one end of the disk. If it moves towards the right, then it has to reach up to 199. And it is not going to touch 0. Now the scenario is opposite. It has moved from towards the left, so it has to move. It has to touch to 0, and but it is not going to touch 199. Either end in the scan. Then once it reaches to the one end of the disk, move the current head position and then serve all the requests which are coming in the path. So likewise, it is going to execute it. This algorithm, that is the scan algorithm. So again, I repeat, the scan algorithms here, the scan algorithm go until the last cylinder. Anyhow, it has to touch any one end. Service in both the direction. Both the direction means it may move towards the right or towards the left, but anyhow it has to touch any one end, maybe 0 or maybe 199. So likewise it is going to calculate the total head movement in terms of the unit as cylinder. So what is the total head movement? 208. Now the next one is the circular scan. As the name itself indicates, circularly scan, and the snapshot shows what is there in the circular scan. Go until the last cylinder and service in only one direction. Now see here, circular scan provides a more uniform wait time than the scan. As the name itself indicates, circularly scan. It has to move. It has to go from one end of the disc to another end. The head move from one end of the disc to other, servicing request as it goes. When it reaches the other end, however, it immediately returns to the beginning of the disc without servicing any request on the return trips. Here, very important in case of the circular link list. When it reaches to any other end, it immediately returns to the beginning of the disc without servicing any request on the return trip. It will not serve the request on the return trip. First, it has to touch the other end of the disc and then serve the next request. Treats the cylinder as a circular link that wraps around from the last cylinder to the first one. So, see here. From this example, we can easily understand the concept of the circular scan. The head start at 53, then it started towards the right. Yes, it can start towards the left also. Then 65, then 67. Serve all the requests which comes in the queue, which comes in the path till the other end. What is the other end? It is 199. Touch it. Serve the end of the disc, that is 199. And once it reaches the other end of the disc, that is 199, without servicing 3714, it has to touch the other end of the disc because it is a circular concept. Once it touches any one end, then come back to the other end and then later on move the head position and serve the next request. The next one is the 14, and finally it has reached, it has touched 37. So likewise, it is going to execute the concept of the circular scan, and accordingly we can calculate the total number of the head movement in terms of the cylinder as unit. Now the next algorithm, that is a disc arm, that is a look algorithm. So the disc arm starts at the first input output request on the disc and moves towards the last request input output request on the other end, servicing request until it gets to the other extreme input output on the disc where the head movement is reversed and servicing continues. Here, what happened in the circular link list? Then servicing the request until it gets to the other extreme input output on the disc where the head movement is reversed and servicing continues. It moves in both the direction until both last input output request more inclined to serve the middle cylinder request. Now see here. Example is the sequence is 176, then 79, 34, then 60, then 92, 11, 41, 114. This is the queue request. What is the current head position? 50. And direction we have assumed right. We are moving from left to right. See here, while solving this numericals, you can assume any direction, maybe towards the right, maybe towards the left. It is not mandatory that always go towards the left or always go towards the right. But here for this numerical we have assumed the direction towards the right. Now output initial position of the head is 50, and after calculating the total seek time in terms of the total or the total head movement is 291. Six sequence, how we got it is 60, 79, then 92, 114, 176, 41, 34, 11. See here. What happened in the look algorithm? First, what is the current head position? It is 50. Then it moves. Let us consider if it has decided to move towards the right, then come to the other end, one end of the disk request. What is the final request in the queue? It is 176, and serve all the requests which are coming up to 176. Once it reaches the final request in the queue, then move the direction and then serve all other requests which are coming in the what we can say path, and reach the final request. So see the difference between the look algorithm and the what we can say the circular scan algorithm. So in circular scan algorithm, we are touching both the end, whereas in the look algorithm, we are simply serving both end request, and accordingly we are going to calculate the total head movement or total seek time. And accordingly, yes, that's I told you that the difference. So accordingly, we have got 291 for this sequence. Now the circular look, it is the version same as that of the circular scan. So see here, just keep this picture in your keep this picture clear. It never, the look algorithm has not touched any one end. It has touched only the final request and then come back, serve the request and touch the initial request. What happened in the circular loop that we are going to see, as the name itself indicates, circular look, surely it is going to touch any one end or two end that we are going to see. Version of circular scan, arm only goes as far as the last request in one direction, then reverse the direction immediately without first going all the way to the end of the disk. See here. See the difference between the look and the circular look. In case of the look, once it has touched the last request, it has served the last request, then immediately come back and serve all the requests which are coming. But in case of the circular look, it is same as that of the circular scan. What is the current head position? It 53. Then start from 53, reaches to 65, means it has decided to move towards the right direction. Then accordingly go for serving up to 183. Once it has reaches the final request in the queue, move the head position, but do not serve 37 and 14. Do not serve 37 and 14. Whereas in case of the look, we have served 37 as well as 14, or rather we could serve 37 and 14 also. So in case of the circular loop, it goes to the other end of the request. What is the other end of the request? It is 14 and then come to the 37. So likewise, it is going to serve the request without touching to the end of the disk, that is 0 and 199. So again, I am showing you the snapshots here. The scan algorithm, any one direction, touch that any one end of the disk, then move the direction and serve it, but do not touch the other end of the disk. Circular scan, start from the head position, take the decision, anyone may be left or right, then go to the one end of the disk, then come back to the other end of the disk, then serve it. Look, do not touch any end of the disk, maybe the 0 or the last one 199, but serve the initial as well as the final request. So this way it is going to execute the loop. But whereas in case of the circular loop, in the reverse case, it is not going to serve. It has to touch the first initial request and then again move the direction. So this way it is going to execute, that is this 4 elevator principal concept algorithm. Now the next algorithm that we are going to see is RS. It stands for the random scheduling. And just like its name, it is in nature. It is used in situations where scheduling involves random attributes such as the random processing time, the random due dates, the random weights, and stochastic machine breakdowns. These algorithms fit perfect for these parameters, which is why it is usually used for analysis and simulation purpose. The next algorithm, the LIFO, last in first out. So what happened in the LIFO? See here, newest job or service before the existing one, that is in order of request that gets service the job, that is newest or last enter is going to serve first and then the rest in the same order. It means the request which comes just what we can say just or which is very new or which has entered lastly, just now entered, is going to serve first and then rest in the order. So what is the advantage? The maximum locality and resource utilization. Sure, it is going to use maximum resources. And what is the disadvantage? Can seem a little unfair to other requests, and if new request keeps coming, it causes starvation to the old and the existing one. As we have seen, uh, the what we can say, the starvation issue in case of the shortest seek time first algorithm or SSDF algorithm. The same concept of the starvation comes in the LIFO, because every time it has to see whether any new request is coming or not. If it comes into the system, it has to execute it, it has to serve it. Then what will happen with the oldest one? So oldest may go into the starvation. And we know that in order to solve the starvation concept, we have the technique that is the aging technique. Aging is used to solve the problem of the starvation. So basically, if we compare all these algorithm, then majorly this LIFO algorithm and the shortest seek time first algorithm, they are sufferer from this concept, that is the starvation concept, because of their definition or because of the concept they have. The next algorithm is n-step scan algorithm. It is also known as n-step loop algorithm. In this, a buffer is created for n number of requests. All requests belonging to a buffer will serve in one go. Also, once the buffer is full, no new requests are kept in this buffer and sent to another one. Now, when these n requests are serviced, the time comes for another top n request, and this way all get requests get a guaranteed service. So ultimately, n-step scan algorithm, it is going to create a buffer, and all the requests which are coming will be kept in the buffer, and then it is going to serve it. So what is the major advantage? It eliminates the starvation of requests completely. There is no starvation as we have seen in the LIFO and SSTF. The next one is the F-scan algorithm. This F-scan algorithm has two sub-queues. During the scan, all requests in the first queue are serviced and the new incoming requests are added to the second queue. Means there will be two sub-queue. Means first, the requests which are in the first queue is going to serve, and the new incoming request will be added to the next or the second queue. All new requests are kept on halt until the existing requests in the first queue are serviced. What is the advantage? Major advantage? F scan along with n-step scan prevents the arm stickiness, the phenomena in input-output scheduling, where the scheduling algorithm continues to service requests at or near the current sector and thus prevents any seeking. Each algorithm is unique in its own way. Overall performance depends upon the number and the type of the request. So, hope so that you have understood the concept of the F-scan algorithm, and just note down this thing. Average rotational latency generally taken as half of the rotational latency. Now, if we compare the various dict scheduling, so many dict scheduling algorithm we have seen. But if you compare these 6 algorithm, major 6 algorithm as far as the disk scheduling is concerned, that is the first come first serve as a shortest seek time first scan algorithm, then C scan algorithm, look and C look. The we need to find out that which gives the better result and which has some issues, so that we are going to see later on. Now if we go for the comparison tells us that first come first scheduling is fair scheduling. Yes, fair in what sense? It is not going to consider any priority. The request which comes first or enter first into the system is going to execute. It prevents starvation. Surely it is going to prevent starvation, because there is no concept of keeping any request in the halt stage, and gives lower overhead. See here again, very important point, that is it gives low overhead. This is acceptable when the load on the disk is light. It has extremely low throughput due to lengthy seeks. Yes, we have seen that is a zigzag effect, and it is going to create extremely low throughput. Throughput means efficiency. Here the meaning of the throughput is efficiency. And the next algorithm is SSTF. SSTF algorithm has higher throughput as compared to other algorithm, means more efficient as compared to the other algorithm, and gives lower response time. Response time means it start responding as soon as we submit any request to the processor start responding. That one is a response time. So lower response time than first come first serve policy. It is reasonable solution for batch processing system. So whenever we want to execute any request in the form of the batch, it is a reasonable solution for the batch processing system. Sometimes it does not ensure fairness, because with this scheduling starvation is possible, and that's why the fairness in the sense that fair priority, fair decision to all the algorithm cannot take place. This policy is generally not acceptable for interactive system. It leads to higher variances of response times. The next one is the scan scheduling. It offers an improved variance of the response time. The drawback of this scheduling policy is that it does not change the direction until edge of disk is reached. Starvation is still possible in the scheduling under a light load. Scan policy is the best one. We can consider whenever the load is less, then it is the best policy. But whereas the possibility of the starvation cannot ignore in case of the scan scheduling algorithm. Then the circular scan, it maintains high level of the throughput efficiency while further limiting variance of the response time by avoiding discrimination against the innermost and the outermost cylinder. The loop scheduling, the main advantage of this scheduling is that it only performs sweeps large enough to service all the requests. It improves the efficiency by avoiding unnecessary seek operation. It gives higher efficiency or the throughput. And finally, the circular look. It gives lower variance of the response time than the look at the expense of the throughput. So we cannot say that this particular algorithm gives the better result, because all the algorithms, scheduling algorithm, they have their own features. But still, if we want that which gives the better result as far as the total number of the head movement is concerned, then the shortest seek time first comes gives better result as far as the total head movement or the seek time operation is concerned, whenever we are going to compare all these 6 algorithm. But see here again, the problem with the SSTF is the starvation, whereas the scan algorithm is the best policy algorithm. But again, there is the starvation problem cannot be ignored. The C scan gives the highest level of the efficiency, whereas it has again some issues. This loop again, it is not going to serve both the end of the disk, though it gives the throughput, highest throughput. So likewise, All the, what we can say, the scheduling algorithm, they have their own features, they have their what we can say, the characterization characteristic. But if you simply consider only one point, that is which gives the minimum total head movement or the seek time operation, then the shortest seek time first is better for this particular topic, that is the minimum head movement is concerned. Now while selecting a ditch scheduling algorithm, yes, uh, we need to consider this many points. SSTF is common and has a natural appeal, because why it has a natural appeal? Because the shortest seek time first algorithm, wherein we do not know that whether the coming request is very close or takes minimum seek time from the head position or not. That is the only issue with the shortest. That means prediction is required whether the next request which is coming is going to satisfy the minimum seek time from the current head position or not. Then scan and circulars can perform better for system that place a heavy load on the disks. Means if you compare, if you simply have a question like if there is a heavy load, then which algorithm is better, then scan and circulars can perform better. Then performance depend upon the number and the type of the request. Request for disk service can be influenced by the file allocation method. Yes, the disk scheduling algorithm should be written as a separate module of the operating system, allowing it to be replaced with a different algorithm is if what we can say, if necessary. And the shortest seek time first or the look is a reasonable choice for the default algorithm. So after going through this scheduling algorithm, we cannot conclude, basically we cannot conclude that this algorithm gives better result. Ultimately we need to find out on which parameter we need to consider this particular algorithm, whether it is a light load or the heavy load of the request, or asking for the minimum operation or the total head movement, or if we simply consider that the starvation problem should not occur, or little bit starvation problem may be considered. So likewise it depend upon the finally performance ultimately depend upon the number and the type of the request. That if we consider the first come first serve, if it is going to execute in a sequential manner, and if all the requests are coming in the sequential manner and do not have what we can say, the zigzag effect, or the numbers are, let us consider 3 4 5 in this way. If the requests are coming, then surely the first come first serve gives the better result, and no problem of the zigzag effect also. So likewise we cannot be a rigid one on this issue. Now, final conclusion is that the performance of the disk scheduling algorithm depends heavily on the total number of the head movement, the seek time, and the rotational latency. On these three parameters, that is the total number of the head movement, the seek time, what is the seek time, and what is the rotational latency. The performance of this six algorithm that we have seen, along with that six we have seen four more also, but we are simply considering the six algorithm. Out of this six algorithm, four algorithm, the scan, C scan, look, and C look belongs to the elevator principal concept. The performance is purely based on these three parameters. With the classical approach of the disk scheduling algorithm, few algorithm like that shortest seek time first and the loop will be the most efficient algorithm compared to the first come first serve, scan, C scan, and C loop disk scheduling algorithm with respect to these parameters. That I have already told you that shortest seek time first gives the minimum total head movement, Along with that, look also gives, because in the look algorithm it is not going to touch the two end of the disc or either any end of the disc, so that much portion is going to be deduct from the total number of head movement. So surely it is going to give better result when we go for comparison with the scan C scan or the C look algorithm. So likewise, it purely based on that what exactly we want. Then but if you compare, if the comparison takes place that out of this four elevator algorithm, that is the scan, C scan, look and the C look algorithm, which one gives the better result? Then surely the look is the efficient algorithm when we simply compare with the other elevator algorithm. And now the final one is the important points to be taken care. Big scheduling is important because of this many reasons. Multiple input-output requests may arrive by different processes, and only one input-output request can be served at a time by the DIX controller. So, though multiple input-output requests may arrive from different process, but ultimately only one input-output request can be served at a time by the DIX controller. So, ultimately DIX controller means without the help of the CPU. So, who manage this input-output? That we have already seen when we seen the concept of the CPU scheduling algorithm, that is a transition diagram, state transition diagram. So the DMA, direct memory access, without the help of the CPU is going to serve the input output request. Thus, other output requests need to wait in the waiting queue, and accordingly it is going to schedule. The next one is two or more requests may be far from each other, so can request in greater disks are movement. If two requests which is coming to be served or for serving purpose, if they are the gap of the disks, what we can say, the seek time or the difference is too far, then surely it is going to have more disk R movement, greater disk R movement. The disk R movement is uh, very what we can say more larger. And finally, hard drives are one of the slowest part of the computer system and thus to be accessed in an efficient manner. So see here, we know that the cache memory, then primary memory, then the secondary memory, and if we simply compare these three memory, so hard drive, that is a secondary memory or the primary, we cannot say it is a physical memory. Physical memory ultimately it is a primary memory. So secondary memory or the hard disk drive are one of the slowest part of the computer system. Is we need to have the efficient algorithm, because so the hard drive, the space, or what we can say, the memory of the hard drive is very huge, and so much data is there, so many folder and files are there, and that's why we are considering it is the slowest part of the computer system. And because of that, the efficient algorithm must be there, the or execution of the algorithm must be taken in a efficient manner, so that the operating system is going to serve or accomplish the task given by the user in a very faster manner. So ultimately that is the only objective that we have already seen on the first PPT. So this way, this disk scheduling algorithm concept is there. Now, again, I'm going to tell you few important points of this algorithm. That is, see here, shortest seek time first. It is going to find out. First come first serve. It is not going to consider anything more fairness, whereas it is going to execute all the request in some particular sequence, but it suffers from the zigzag effect. Shortest seek time first takes minimum seek time from the current head position. It is same as that of the shortest job first, but the issue is that it causes the starvation that we have already seen. Then these four are the major algorithm which belongs to the elevator principle: scan, look, circular scan, and circular look. Scan algorithm, it start at one end of the disk, moves toward the other end, service request until it gets to the other end of the disk, where the head movement is reverse, and then service continues this way. Then circular scan, again move, start from the head position, move, serve all the requests which are coming in any direction, might be towards the left or right, touch the other end of the disk, then reverse the head position, touch the other end, and then serve the request, and then continues the request. The look, start from any direction, then request the final end of the what we can say the request. Here from this chart, we from this request we come to know that 176 is the final request. Then change the direction, and then serve continues. Whereas the circular look, same concept as that of the circular scan, but without touching any one end or both the end of the disk. And then we have seen RS, the LIFO, which is going to serve the request which comes just now. So it suffer majorly from the starvation problem, because we cannot predict that the new request which is coming has the smallest what we can say coming or not. Likewise, we have seen the n-step scan algorithm, then f-scan algorithm. Then we have seen the comparison of all these algorithms. Then selecting the disk scheduling algorithm, these many parameters, and then finally the conclusion. So ultimately, when we compare this algorithm, so if you simply consider only one point, that is the minimum head movement, then SSTF is the better one. But otherwise, all algorithm, they have their own characteristic, they have their own features. So we cannot simply say that only this algorithm is far better as compared to other one. So with this, I conclude my today's topic, that is the disk scheduling algorithm. Thank you very much.